Hello guys, welcome to the Innovation Lab. In this video we're going to be conducting the initial testing on this high power DC to DC boost converter concept that I mentioned in my last video. Alright, I know that a lot of you guys have been asking about how you can possibly boost the output capacity of your DC to DC boost converters. That way you don't have the manufacturer set limit kind of setting you back or limiting you from the what you can do with these converters. And that was actually what led to our last video where we tried to connect these DC to DC boost converters in parallel. And as we had anticipated, the outcome of that test was not very good. It actually led to one of the converters failing multiple times, and we had to keep on repairing it, but still in the end it didn't give me satisfactory results. So I told you guys that I would try a different concept, which is what we're looking at here, and I'm gonna go ahead and explain what we're doing here so that way it makes sense to you guys as you try to follow along with this project. Alright guys, in this video we're going to modify the format a little bit just to keep things interesting and fun and also exciting. So what we're gonna do is to show you guys the output voltage test first. Then after that we're gonna explain the concept, and towards the ending we will show you guys the output current test, which is also a load test that we're gonna be conducting on this setup. Also, I'd like to mention that this video format is going to be longer than our usual videos, and the reason for that is that we really wanted to take some time to explain this concept for those of us who may be interested in doing something like this in the future. So we don't want to rush through it. So if you are in a hurry, you can skip through the video and get to all the different sections that you are interested in. So in my opinion, taking the time to explain everything will be something that will have a good value to anybody watching this video in the future. Alright guys, in this first video we're just going to be introducing the concept, and right after that we will conduct a couple tests. One will be the output voltage test, where we try to vary the output to about 90 volts just to make sure that the system performs well as a boost converter. And the second testing will be the output current test, where we put a load on the system and we make sure that we can still vary the output current using the potentiometer that we have on the control board. And in subsequent videos we're going to be performing the efficiency measurement. We can't do it today because we don't have the right power cables to conduct that test efficiently. And also we plan to do efficiency comparison measurements between the original converters and this board. And we also have a second converter here that we're going to be testing very soon, and we're going to be comparing the efficiencies of each of these converters with the one that we're building. And if you like to see all of this, if you're new to our channel, please make sure that you subscribe to the Innovation Lab. Alright guys, let's get started. Alright guys, as you guys can see here, we have applied the input power. So we are using the server power supply, which comes in at about 12.3 volts with no load, and we're bringing that to the input of our converter, and our output is already at 26 volts from some earlier testing that I was doing. And now let's go ahead, and first of all maybe we should bring it all the way back down so that you guys can see it. we're going to bring it all the way down to the same input voltage level. All right, right now we are at, we actually went down below the input voltage. I guess the system is working too well. So now we're at 13 volts. So we now increase the output voltage to see how high we can go. This is the very first function of a DC to DC boost converter, which is to take an input voltage level and boost it up to essentially wherever you want it to go. So let's see how high we can take this. So right now we just crossed 50 volts, and our goal would be to get to around 80 to 90 volts. And all right, we crossed 70 volts. Okay. All right. Getting a little nervous. All right, so right now we are at 90 volts. So we have 12.3 volts coming in, and we have an output of 90 volts. All right, let's take it all the way back down for our first load testing for the next test that we're going to do. So our goal is to get to about 28.2 volts. All right, so we're at 28.5. I think that's good enough. 28.4. So this is what we're going to be using to charge our 24 volt lithium phosphate battery pack. So we have 12 and 12, and we're going to use it for the next test. All right, so the first test is a success, and I am super excited. All right, so what we're actually trying to do here is very simple if you understand the concept. So since we have shown that individual DC to DC boost converters, or SMPSs in general, doesn't really like to play well when connected in parallel, and there is a simple reason for that. The reason for that is each of these switch mode power supplies, when you connect them in parallel, each one has a control loop and a feedback loop that tells it, what's going on the output with regards to when load is applied. So what happens is, even though you set the output conditions to be the same output voltages, the same output current levels, so what happens is that as soon as you apply load, one of the boost converters that has a faster response, or we call them loop response, will try to take over all the load. And by so doing, it kind of wants to drive the entire load, and if it can't, then we have a failure on our hands. And if care is not taken, with that converter gone, the next converter might want to do the same thing, and you may actually have the two converters failing. But luckily for us, during our test, we only had one converter that failed. So that's the problem there. So what we are proposing as a way to solve this problem is to essentially move the major components of these two converters. So we merge them on one board. We move the power inductors, we can call them A and B, and we move the drive MOSFETs, A and B, and also we take basically all the major components, the fuses, this here is like the output current sense shunt. So we moved everything and we kind of consolidated them on one board here. So as you can see here, we have the 2 power inductors. In this design topology, it wasn't really what I set out to do, but I had to do this because I had some noise concerns for my original design. I'm still going to do that in the future. But what we have here now is essentially 2 inductors that are connected in parallel. And I have 2 MOSFETs that are driving the inductors also kind of connected in parallel and to each other, but their gates are individually isolated using a small resistance. And I'm going to show this in the schematic that I put together. So, and here I had connected the 2 current shunts in parallel to help us adapt to a higher power without having any malfunction there. So then I changed the fast recovery rectifier diode to a value and a different package that will give us actually a higher output current without being overstressed. So with all of this on one board, now what we're doing is, instead of having 2 control loops, so what we have done now is to use one single control loop from one board, from one single PWM chip here, the TL494. And so we kept everything the same way it was. So we maintained that function, that PWM control function. So we're taking it and we're bringing it into the board here. We're taking the current sense and we're taking the voltage feedback and the current feedback loops. We're taking it from the board and we're bringing it over here. Actually, we're taking it from over here and we're bringing it into the control board. And we're going to increase our input fuses from 60 amps to about, we have enough space here to where we can actually increase this to about 100 amps. One of the additional steps that I took to make sure that this concept will be a success, especially the way we are running it, was that I added a MOSFET driver to help us clean up the PWM pulses that will be coming from the control board here. So basically, looking at this, we are kind of breaking a lot of rules and doing things that are not really advised for EMI noise shielding. You're not supposed to have free running wires like this in a high frequency power system like this. But then we took some precautions. As you can see here, we have all the cables that we're using twisted, positive and negative. At least we have a ground cable twisted either on the signal lines or the positives. So that way, that will help us cancel out some EMI noise that each line may be carrying. So the one last thing that I added was this EMI shield here. And I added it because in a high frequency power system like this, especially when you have this unshielded toroidal inductors, they tend to make or generate a lot of EMI noise, which is not good for components within the proximity of the magnetic field. And so we had to find a way to shield it to protect the MOSFET driver and some of the other components that are in here, the power MOSFETs, the rectifiers, and some of the biasing resistors that we have in there. The EMI noise is not going to damage those components. The concern is that we don't want that noise getting on the control signal, because then that could cause the MOSFETs to malfunction. So that was why we added this. So, and to be really fair, this was not something I properly designed. I just wanted to add something just to help out a little bit. I am not even sure that we should be too worried about EMI here, because the switching frequency of this control board only goes to about 100 kilohertz. So I don't know. I don't think that should be much of a concern, but it's also good to be safe. Actually, if this was to be a properly designed board, power board, so we will have multiple layers, and we basically have to bury those signals between some layers of grounding, so that way they will not actually see the noise. Yeah, so that is the design concept in a nutshell. All right, guys, the next test that we're going to be doing is the load testing. So again, we have our 12.3 volts coming in from the power supply. We boosted it up to 28.4 volts, and we're going to be using it to charge our lithium phosphate battery pack. So here right now, because there is no load on the system, you can kind of see the system is basically running at a very low duty cycle for the PWM. So the moment we plug in a load to it, you are going to see the shift, a slight increase in the on state of the control pulses. All right, let's go ahead and do that. And when we have the load on, then we go ahead and slowly increase the output current of the system, or the charging currents that we're going to be using for these batteries for this test. All right, let's go ahead and plug in. All right, the battery is connected, and as I mentioned, we have clean drive pulses, and as you can see there, the duty cycle of the PWM just increased to show us that we actually now have a load on the system. What we're now measuring is the battery voltage and the charging current, and we're putting about 14.2 watts into the battery. All right, so now let's go ahead and increase the charging current by adjusting this potentiometer here. And that's another test that we're doing to show that we can still control what's happening on this board using their original circuits or circuitry that we have on this control board. So everything stayed except the major components. All right, so now let's go ahead and adjust our output current potentiometer, and let's see what's going on over here. All right, as you can see, our output charging current is increasing. All right, as you guys can see, at this point, we're putting out 10.8 amps at about 304 watts going into the battery system. But before we proceed, let's go ahead and turn on the fan so that the MOSFETs and the rectifier doesn't get overheated. And it's pretty much gonna get loud, so I won't be able to comment. Alright guys, since things are going so well, all the tests that we have performed gave us really good results. So I kind of got really excited and I wanted to try one more test just to prove that this concept really works. And what we're trying to prove here is that we saw earlier that this converter could only give us about 300 watts at a 12 volt input. So what we're going to try here now is to give it a 12 volt input and see if we can get our target for this will be about 500 to 600 watts at the output. And then we're going to see how the system is going to handle that. So to be able to perform that test, I am using a different load now. So here I'm going to be using our 1000 watt resistive heater. So this heater gives us a constant resistance value. So the way we're going to accomplish our load stepping will be to increase the output voltage that's going to go to our heater. And as you guys know, going by Ohm's law, as we increase the voltage across the heater, we should also expect that the power dissipation on the heater should increase proportionally with the increase in voltage. Alright guys, let's go ahead and conduct the test. Right now our output voltage is at 28.4 volts and our target voltage should be about 48 to 50 volts. That's when we should expect a 1000 watt dissipation on this heater, and we're not going to drive it all the way to 1000 watts, but we're gonna see how much. We keep an eye on the power meter to know when we get to about 600 watts. All right. Alright guys, that's it for this video. And looking at the tests that we just conducted in the end, so we can kind of summarize the test that we conducted into an output voltage test and an output current test. So with the output voltage test, we have shown that we can take an input voltage level of 12.3 volts and boost it up to about 90 volts using this boost converter system. For the second testing, which was kind of a load test, we put a load on the system to see if we can still vary the output current using this potentiometer that we have on this control board here. And that also allowed us to see if this system can still, to a good extent and tolerance, regulate the output voltage, because that's one of the core functions of a well-regulated converter. Also, as we have seen during the last load test, we were able to get to an output power level of about 500 watts that we use to drive our resistive load. Yes, we were not able to get to 600 watts, but getting to 500 watts with a 12 volt input, in my opinion, is still quite impressive. And that goes to show that this concept actually works. So basically, we have almost doubled the output power that we would have gotten from a single DC to DC boost converter. Alright guys, as I mentioned earlier, our goal for this video was not to conduct an efficiency measurement, because we don't have the right equipment to do that. We don't have the right cables to do that. As you can see, looking at the 2 meters, you can kind of see that there's a lot of cable losses. Looking at the voltage difference between these 2 meters here, we have 12.1 here and we have 12.6 here. That tells me that we're losing a lot of power here, and these cables are not the right cables to use for an efficiency measurement. But even at that, looking at the numbers that we measured during the load testing, we were able to provide a 327 watts going into the battery. And to do that, we took in an input power of 405 watts. So that gives us right around 80% efficiency, which I still think at 12 volts, it's not too bad. Alright guys, that's it for this video. In the next videos that we're going to be making on this concept, we are going to be conducting this test using a higher input power and input voltage level to drive this system. We just received a couple more of these 750 watt server power supplies, and the goal is to have them all connected in series, and we're going to use the series configuration to make a 36 volt power supply that we're going to be using to drive the system. Alright guys, I hope you had some fun watching this video. I hope you learned something from the video. And if you did, don't forget to give us a thumbs up. Don't forget to subscribe to the Innovation Lab so you get notified as we release the future videos. Alright guys, I'll see you guys in the next video.